Hi there, it's Z here, and welcome to the final video in a series of videos that I've been making around using the tools of linear programming to help optimize capital budgeting. If you've just joined this, you will definitely want to go back and scan through the videos that precede this one. And if you've come from the previous videos, then welcome back. And as a quick recap, we've looked through a series of scenarios that have increased in terms of complexity, and we've made use of a number of different tools, ranging from the native solver in Excel to add-ins like OpenSolver to Solver Studio, and also we've looked at code-based solutions using Python libraries like PulP and Pyomo. Now, what we're going to be doing in this video is we are going to be exploring the use of a commercial tool called Frontline Analytic Solver. And this is a tool that is made by the same people who've created the basic solver model in Excel, and they have a premium product that is available at a cost. And at the time of recording, this gives you a bit of a feel. So you do have to be willing to pay for what you're gonna get. But as I will show you, it's quite a nice package, and this is an overview of how it works. It's got more than just optimization. It also does risk simulation. It's got data mining. So it's quite a nice package that has a very broad range of functionality. If you can afford it, that is, and if that's what you need. They've also got documentation online on YouTube that you can look through. So being commercial, I guess they've got a bigger budget in terms of organizing and explaining how their kit works. So I signed up for a license, and let me just show you how that works. So it adds in this uh, additional tab in your Excel sheet. And it's taking a bit of time because it needs to talk to the license server. Okay, here it is. So, oh, so let me just go to the scenario that we were talking about. So where we last left off is we were looking at scenario number 5. And if you recall, scenario number 5, what we did in scenario number 5, let me just close this so it's not distracting, is we did two things. We tried running a loop for understanding what is the best uh, set of decision variables in terms of which year to place the projects, given a certain uncertainty for capex and uncertainty for the benefits. And how we solved it is we use a loop, and we tried both Excel and Python PulP, and in PulP, it was a lot faster than Python. So I'll just show you, sorry, it's a lot faster than Excel. And I ran 1,000 iterations here, and we sorted the information. And what that allowed us to do is to produce a histogram where we can see all the different, it's kind of tiny, but these are all the different permutations in terms of project 1 to 10. What is the frequency of occurrence of a particular configuration? And what we could see is if you run it 1,000 times, about 166 times, this appears to be the most optimum solution, where project 1 is year 2, project 2 is year 4, project 3 is year 2. So this is just a string of which year which project takes place in. And it took us, like the code said, about 8 minutes to churn through this and get an answer. And we're going to see how this commercial package works, and whether it's any faster. So this is identical to scenario number 5. And how this has been defined is the model is uh, built using something that looks a little bit like the native Excel solver, but with more bells and whistles. But basically, what I've done is I've defined some uncertainty variables using Analytic Solver's native uncertainty functions rather than Excel's. So you can see that this is a psi PERT, which is the formula that the analytic solver uses, and it just refers to the cell. So I don't even have to calculate alpha and beta. I just need to put min, mode, and max. And I've also done the same for the benefits, and the numbers jump around every time you click, like that. And I've put in the decision variables, where these are decision variables E3 to E12, and I've also set up a objective variable, and here you see a note that says expected, and you have to select because this is probabilistic, you are trying to optimize for the average expected value. There are other options that you can choose. I'll talk about it separately, but we're trying, and in this case, we'll keep it simple. We're trying to optimize that such that the decisions on average will produce the best sum of all the benefits over that 3-year period. So the other constraints are identical to what you saw before. Now, those of you who saw the previous video will also realize that unlike how I did it last time, I'm actually referencing the cells directly rather than what I did in the previous model, where I had to sort of cut and paste a static version every single time per iteration. I don't have to do that here. Now, sorry, jumped around. So I'm going to run this, and we're just going to see what we get. Now, at the same time, I'm going to blank it out just so that it's a fair. I don't think I've cheated in any particular way. Okay, so this cell is just basically a calculation, and right now it's all false because everything is blank. So it's just a easy way to have a look at which year each project is selected on. Now this number is a cut and paste from the PulP file, the PulP result that you saw a moment ago, where we looked at the most frequently occurring solution. And now we're going to crank the handle with Analytic Solver and see what comes out. So I'm clicking optimize, and we'll see how fast it takes to churn through the answers. And part of the power behind this package, and probably why it's so expensive, is there's been a lot of work in the background to help speed up simulations, where rather than doing what we went through the last time, where we're simulating every single iteration, there is a tool that Analytic Solver uses where it interprets the underlying model logic and simplifies it, and it does something called a stochastic transformation, where rather than try and build up iteration by iteration, it actually looks at all the different variables, constraints, and it can transform your model into a deterministic equivalent and solves it. And because it's deterministic, it's a lot faster. Now, you can see that the solve time was 20 seconds compared to the 8 minutes from doing it in iteratively using PulP. And we get this sort of shape in terms of which project, which year. And let's have a look at what it looks like. You can see that the results are identical. and we've achieved it in only a fraction of the time that it took. So it's pretty impressive. So there is really something to be said about splashing out on a commercial tool rather than trying to DIY everything from open source tools. And we'll do one more thing before we go to our very last variation on the scenario. We'll look at what happens. So now we fix the decision variables, and we're going to see how this affects the overall probabilistic benefit over 1,000 iterations. And how we do that is we run a simulation where is it working, stinking. So my only complaint with this platform is sometimes it takes a bit of time for it to crank the handle. I think I've got it working. Okay, so I am going to maybe expand this a bit and move this here. So I'm interested in AD14, and I know it's AD14 because AD14 is the tab that has the overall result. And what this curve is showing me is if I fix my decision variables to those what is supposed to be the most optimum, and I want to satisfy all the constraints under all the probabilistic outcomes, this is the range of results that I can get for my maximum benefit. And I can take a P 10, 50, 90, an average or whatever it is that I want, and have a look at this. And I can even remove certain constraints and see what it does. So the package that Analytic Solver offers is comprehensive in a sense that you can use it for all the different aspects that you would need to analyze, not just come to a optimal solution, but also back analyze what it does. So we're going to carry on with a final example that is a bit more complex, that brings together everything that we've seen, but I'll be using Analytic Solver because it has the sort of bench strength to do a whole bunch of different things. So this is the model setup. It's similar to what we saw earlier, but now it's got a whole bunch of additional constraints. Like example, simple one is we've added some correlations to the model where the capex variability for it's capex, sorry, this one. The capex variability for projects 1 to 5, so this is column R, column Q, has a strong correlation. So if projects 1 to 5 tend to be, they tend to move together in terms of whether they are expensive or they're cheap. There is a negative correlation between projects 5 and projects 6, so that if the benefit of project 5 is high, the benefit of project 6 would tend to be low. So that's these two cells over here, and so on. So we even have variability on the capex thresholds. So rather than do a static capex threshold, as you saw in the previous example where it was always 30 or always 25, in this example now, you have variability in the capex threshold itself, where instead of a fixed value, you can see that instead of 30, it uses a distribution, again, beta PERT, for this year, and the distribution gets wider for the third year. And that kind of makes sense because the further you are in the future, the less certain things become. And we also have some of the conditions that we saw in scenario 3, where projects 4 and 8 must always happen at the same time. Projects 4 and 8, I've set constraint where these cells, you can see in these cells where E6, E10, F6, F10, and they have been set so that they must always be together 0 or together 1. And we also have a case where 5 and 10 are mutually exclusive. And I've done that using some helper cells where this cell adds together these two cells. And because they can never happen in the same year, this must always be 1 or less. And you can see that here where this is 32, so F32 is less than 1, G32 is less than 1, and we also have project 7 is an option only if project 2 is complete, where project 7 cannot happen unless project 2 has been completed. And I've set that up using constraints as well, where example, I've made project 7 never able to start in the first year. So if you look at E9, E9 is a constraint where E9 must always be 0. So it's a bounded constraint. The nice thing about um, the setup the Analytic Solver has is you can turn a constraint on and off just by clicking a button. So that's been quite convenient. This is a bit more realistic in terms of the amount of complexity that you would expect from a real life portfolio. And 10 projects isn't that much, but I can see how this could easily scale up to about 20 to 50 projects that probably would be representative of what you'd see in a big organization. Now, that said and done, I'm going to try and run the optimization and we'll see what comes out and if it falls over. So it's thinking, getting a bit of an error message here, not sure why, but seems to be able to optimize. So it's running in the background. It's taking a bit more time, and that's likely because I've crammed in so many more additional constraints and complexities into the model. And again, it's managed to do a stochastic transformation, which means it's not trying to do it iteratively, but it's solving it using an equivalent deterministic model. And I think it's done. So let's just have a look. And we can now see that it took 6 seconds. Felt longer than 6 seconds, but oh, sorry, 44 seconds. Not so bad. And you can see that the results look a bit different from before. So it used to be this. This was just something I stuck in just to make sure that the numbers don't keep changing, and it comes back to the same result if you run it again. And just like before, you can view a report for the different, if you stick with this, you can have a look at what it does for the different outputs. Like in this example where this is a report that tells you details about how what sampling technique was used to generate the random numbers, and for the given optimum decision that you've selected, you can also see what is the net result in terms of your overall benefit. You get the whole range. You can also look at it in a chart, obviously. So if you want to, you can also, rather than look at summary, you can also step through the simulation, meaning you roll a dice every single time just to have a gut feel of whether the model is behaving the way that you want it to behave. And it does appear to be doing that because 5 and 10 in separate years, 4 and 8 in the same year. 2 was selected, but 7 never got a chance to be selected because 2 was put into the final year. So 7 is put into year 4 plus plus. So hopefully this gives you a feel of what Analytic Solver can do. In fact, actually, there's a lot more that is available on this platform because I haven't even began to explore things like probabilistic constraints. Because what you can do is you can set a constraint so that rather than following the constraint all the time, you can say that for 95% of the time it must be within a certain range, and 5% it can be beyond. You can set sort of multi-stage probabilistics where what I've currently done is we're making a decision on all the year 1, 2, 3, and 4 beyond at the same time. And the dice roll, if you like, for the capex constraints happening uh, in a probabilistic fashion. A recourse variable allows you to make decisions for a second stage after the dice has been rolled, and these are in a way treated as static numbers rather than risk numbers. It's a complicated topic, but definitely an interesting one that I've not come across before yet. So I probably won't have time to cover every single detail, and I'm also still learning this, at least for as long as the trial license lasts. But there is quite a lot of documentation. So this is available online. I think if you just Google search it, you can probably find it, and it's a whopping 500 pages. They've got their own learning academy as well, so you're welcome to explore this for yourself. So that brings me to the end of this particular scenario. Now stick around because I'm going to do one final video that rounds everything up. Right, see you in the final video. Bye now.